All right, friends and neighbors, time for us to start talking about the transport layer and a very important architecture that lives up there called the client server. Now, before we dive into layer 4, let's do just a little bit of review. The critical ideas here are what goes on the different layers in terms of addressing, protocols, and equipment. We know that generally speaking, we have three kinds of addresses. We have MAC addresses, IP addresses, and then we have port addresses. And this is not to be confused with physical port addresses, but really we're talking about layer 4 logical ports. Now, if we move up through our layers, we know that the physical layer does all of our electrical and mechanical specifications. That layer 2, our link layer, data link layer, is responsible for really two kinds of things. There's two sublayers there. We have the media access control layer and we have the logical link control. Media access is exactly what it sounds like. We are trying to figure out when it's our turn to talk and for how long, and can we send a transmission. The logical link control is about building the frame, providing the addressing, and doing a little error control. At the IP layer, really this makes a special distinction, because when we are at layer 2 and we're dealing with just MAC addresses, we can use MAC addresses to get to most of the nodes on the network. In fact, if we were just talking about a local area network, you could argue that you don't need IP addresses at all. But the minute things get a little bit larger, we need an additional layer of abstraction, so we have IP addresses. And IP addresses are really about getting us to another network entirely. And of course, at that point, we also need a routing function, and we have a whole different header for our IP addressing and then the operation of the IP protocol. Well, okay, so we can figure out how to get around our local area network, and we can maybe figure out how to get to a destination network with our local area network protocols and our layer 3 protocols and our different kinds of addressing. But that doesn't help us at all with getting to a particular application or software process. And for that, we need something else. And that's what ports are all about. So ports get us to that final position. So we got it to a particular node, MAC address, and that node has an IP address. And so the node says, yep, that's my MAC address. Let me open up the IP packet. Okay, I've got all of this data. What do I do with it now? Well, now we're going to send it to all of these different ports. And so that's where the transport layer comes in. Really, really important. And then, of course, when we get to the application layer, and it doesn't really matter whether or not you're talking about the OSI model with its session, presentation, and application, or the TCP/IP model that sort of folds all that into one. Really, the important thing there is that now you've given it to the application, and we're going to figure out a way to format the data and provide user displays and user input for that particular application. All right, let's talk a little bit about packet processing. If you've been in any of my classes or listened to any of the videos on this channel, you know that the very first thing that a node does when it wants to send a transmission is process its host routing table. And that's the beginning of our building a particular frame. And after that, of course, we move on to the ARP table, and whether or not we need to ARP for the destination or the default gateway. Now, once we decide how to build the frame, we're going to send this thing off to the network. And the first thing that we're likely to run into is a switch. And the switch forwards things based on MAC address. The switch really doesn't care about anything else. So the switch processes the CRC at the end of the frame, populates the source address table, and forwards things based on where it believes the destination MAC address lives. Okay, so now we get beyond the switches and we wind up at a router. Well, the router doesn't care about really the layer 2 frames at all. All that it's interested in is whether or not it was a broadcast frame, remember at layer 2, or its own MAC address seen in the destination, in which case it'll open it up. Now, of course, if you send something to your default gateway because you're looking for a destination that's not on your network, that's when you're going to use the MAC address of the router. Okay, so now the router gets it, opens up the frame, looks at the IP header, says, where are you going? Let me see if I know how to get to that particular destination, and then forwards it out the proper interface, or forwards it to another router or its own default gateway. But we still haven't gotten to the destination node or the destination application process. So this proceeds all the way until we get to the destination network. Well, at that point, the router says, well, I know where the destination network is, and in fact, I'm directly connected to it, and I might be able to ARP for the destination. So the router can dump a frame right to the destination that you were looking for. So the message that you sent finally gets an Ethernet frame addressed to the destination with the correct MAC address. Then it gets to the correct IP address on that machine. And then we need the port level to get to that particular application. So that's really what we have to think about this, packet processing from source to destination. It's really all about the tables along the way, but once you get to the end destination, you've got to figure out a way to get to that application. So the client or the source has to have a way to provide addressing to that particular destination. And we'll see how that works here in a little bit. I've sort of hinted at this, but why is the transport layer needed? So to remind us, right, an IP address gets us to the right network. But that's all that the routers between you and the destination can do. All that they can handle is the layer 3 routing function. Now, a MAC address, when it finally gets there, is used to get it to the destination node. So we build a frame with the MAC address of the destination, and we can forward it to that endpoint. Okay, so the destination gets a frame, says, yep, that's my MAC address, opens it up, yep, that's my IP address, now what? So the data has to be delivered to the correct process. And as you're probably aware, every node that's out there can have a whole bunch of processes going on. You might be in a Zoom session. You might have a game going at the same time. Instant messaging. You can have a browser going at the same time. So all of these are different processes. If all of those have been sent to your node with the MAC address of your node and the IP address of your node, how do you separate them all? How do they all get to the right windows or the right applications? And the answer, of course, is the port number. So the port number is used to get it to the right application process on the machine. Now we have two protocols at layer 4 that we use to handle this. The user datagram protocol and transmission control protocol. Now they're fundamentally different in their operation, but the thing that they have in common is they both use ports for whatever they're doing. Now in the IP header, there is a protocol ID field. So if you remember, when you were learning about how Wireshark processes things, how does Wireshark know that you're carrying an IP version 4 or an IP version 6? How does it know that it's TCP or UDP? Well, going all the way down to layer 2, we see that there is a frame header. And in the frame header, there's a type field in there. And that tells us what we're carrying in the Ethernet frame. Well, an IP packet has a protocol ID that tells you what it's carrying. And so then you open up the header, whether it's TCP or UDP, and there's a port in there. And that tells us how to get it to the final destination. The two documents that we go to all the time for all of these definitions are RFC 1122 and 1123, but also ITUT X.200. And these are the two documents that contain really the definitions for all of our models. So from 1122, we get that the transport layer provides end-to-end communication services. So it's not just about getting it to a node. It's not about getting it to a network. It's about getting it to the final destination and originating that transmission at the final source. And so really what we're talking about here when we say source and destination is application to application. That's a really, really important idea. And of course, we have the two protocols there. Right from the RFC, we say that TCP is reliable connection-oriented transport service and UDP is ConnectionLESS. Now, we'll talk a little bit more about what that means here in a second, but that just underscores that they are fundamentally different protocols. Now we can get a little more information from ITUTX.200. The big difference between the two documents is that ITUTX.200 doesn't specify protocols. It talks about ideas. In this document, we find that the transport layer provides transparent transfer of data between session entities, right? Because remember that above the transport layer, the first thing that we run into is the session layer, and relieves them from any concern with the way in which reliable transfer of data is achieved. So the concern here is, how do we control or understand that we've gotten all the data that was transmitted? So all protocols defined at the transport layer have end-to-end significance. And again, that is really important because we're talking about application to application, getting it from the original source to the final destination. Now, I am fond of saying that the OSI model is nice to use to understand how things connect together, but for the most part, we don't use the OSI model when we talk about actual protocols. Most of the actual protocols that are in use come from the IETF and all of the RFCs that we've come to know and love. And TCP and UDP are no different. So TCP is outlined in RFC 793 and UDP comes from 768. And this is where we find the operation fully described for these particular protocols. So RFC 1122 says these are the two guys, and then we go to the individual RFCs to see how they operate. Now in RFC 793 for TCP, we see that the discussion is about a couple of really important ideas. TCP is very concerned with a couple of things: a very graceful setup and a very graceful teardown. So we have a connection handshake and we have a teardown handshake. In addition, data is tracked through the entirety of the conversation using sequence and acknowledgement numbers. So each side of the conversation knows exactly what's going on with the byte stream. UDP, by contrast, is connectionless, meaning that it doesn't care about any of that stuff. No connection handshake, no teardown handshake. Each packet is almost a distinctive event. So what this really means is that UDP is largely a command and response protocol. Can I have this? Sure, here you go. Or, can you answer this question for me? Here's your answer. We're done. So DHCP and DNS are really, really good examples of command and response. You ask questions and you get your answers, and then the conversation's over. If we added a handshake to the beginning and the end of those conversations, it will double or triple the number of packets we actually needed. Now, TCP is not command and response. So most of our applications that involve transfer of data or long conversations like FTP or what you do when you access a web page are TCP, because there's a lot more going on and the conversations are longer. But the things that they share in common, the ports and the model that we're going to talk about, which is client server, apply to both of these protocols. So to be really clear, when somebody's talking about connection-less versus connection-oriented, well, what they're really talking about is whether or not you're worrying about the data and whether or not you're concerned about the care and feeding of this connection. As we said, UDP doesn't really do any of that stuff. UDP says, I've got this question and I want an answer. And so the conversations are very quick, usually just a couple of packets. But TCP is very, very worried about not only are you ready to communicate, because I'm ready to communicate, are you ready to be done, I'm ready to be done, but also, I sent you data, did you get it? How much data did you get? Did you send me data? Here's how much data I got. Do we have everything? Is everything in order? Okay, let's put it all together. Thank you very much. And then we'll continue with the conversation. So there's a huge difference in the behavior of these two protocols. And this is in some way reflected in the header. The UDP header is only 8 bytes in length. And the TCP header starts at 20 bytes, but then we have all of these options that we can use to expand the functions of TCP. Well, this has been a little layer 4 review. And of course, we did a little review of the other layers before that. Remember that the important ideas here are addressing, protocols, and the equipment that we have at each one of those layers, most notably routers and switches. We talked a little bit about where our ideas come from, these important documents, RFC 1122 and 1123, and ITU-T X.200. We also reminded ourselves a little bit about what connection-oriented versus connection-less means. Now, the two main protocols that we see at these layers are TCP and UDP. And in the second part of this video, we will talk specifically about the client-server model. Thanks for watching. Thanks for listening. And hey, whether you're worried about them getting there or you're just going to send them on their way and say good luck, I hope your packets always reach their destinations.